I'm Luis Daniel del Campo Armas, and I'm going to talk about the DC shunt controller motor. Well, first of all, I gotta say that before we had variable voltage controller, DC controllers, the only way to control a motor, a DC motor, was by using a different type of connections from the DC supply voltage with a fixed voltage as well, and well, its connection with the motor. This connection had two ways to connect it: the series one and the parallel one. The parallel one is known as a shunt controller, and that is the one that we're going to talk in this session. First of all, the both controllers have no difference or barely any difference on their energy converting capabilities. The only thing is that the shunt control motors are said to be good for a constant speed applications. Another thing that comes with the shunt controller is that it behaves different from what will be commonly thought. For example, if you reduce the voltage in the shunt controller, it will be thought that the speed of the controller will decrease. But instead of decreasing, it increases. This happens since if the voltage helps, the field current and the armature voltage will help as well. Thenceforth, the flux will help since the magnetic flux is not saturated. This meaning that since we have the half as much of flux, the speed will be the same. Or if we have a lower magnetic field current, we will have an increase on the speed of the motor. This can be easily explained in this drawing. Well, first we have here our circuit, which is entirely made of, well, as simple as this. We have a field-controlled current, a resistor, and a field coil that both are connected in parallel to the motor, which will be here the armature. Now, the thing that we were talking about is that once that the field of current reduces by reducing the resistance of the field current controller, there will be a decrease in the back EMF, as we can see here. However, this will have an opposite or not this reaction by reducing the field current, and this reaction will be presented in the voltage, in the voltage of the armature resistance. This voltage will increase for a moment, and then for in some and by passing the time, it will slow it down and then remain on a constant on a steady state behavior. So once that this armature, this voltage that is produced here inside the armature, that will be actually presented exactly in this resistance, we will have as well an increase in the current of the DC motor. And by this increase of the current, we will have an increase of the torque, and we will have a decrease in the speed. So now we're going to simulate it to prove it. Well, now that we are here in the simulation, we can see, as we said before, first we're going to run the simulation, and we get here that the speed that we get is about 144.2 radians per second, the armature current of 0.6, and a field current of 0.8 amperes. Here in the chart, it can be seen that actually the signal, the speed increases while the armature of the current decreases. So as here we can see this as a response of the back EMF and the initial current needed, or the overall current to start moving the motor. So what happens next when we reduce the field current of the motor by reducing the resistance? Well, we only reduce it from 20 amperes to 7 amperes. We run it again. And now we can see first that the speed reduces, as it was said before in the on the chart that was shown. The armature current had a slight decrease. It was 0.6 before, now it's 0.59. And the field current is now 0.9. In the chart, we can see that this behaves again, as it was said before. We have a starting outward necessity of the armature current for becoming or over becoming the static force of the motor, and once it is braked, the motor reaches a steady state and a steady state speed, which will remain constant at all time once that the curve stabilizes. Well, I hope this video was useful and actually helped to understand better. Thank you for your attention.